Hello everyone. In this video we're going to talk about the mud window. The mud window is the interval in which we can drill a wellbore and this wellbore is going to remain stable. As we have seen from previous videos, if your mud weight is too low, that's going to produce shear failure around the wellbore known as breakouts. On the other hand, if the mud weight is too high, the pressure in the wellbore is going to be uh, high enough so that you may cause a tensile fracture and after a hydraulic fracture in your wellbore. The interval in between is the mud window. Now we're going to add a few more practical concepts in order to determine this mud weight and this mud window. And for these practical considerations, we're going to add as a determination of the lower bound for this window, the pore pressure. Before we consider the stability of the wellbore, taking into account the presence of shear around the wellbore, now we're going to add pore pressure. And that means that sometimes if we go through to a pressure in the wellbore which is lower than the pore pressure, then we're going to have a gradient of pressure going from the formation to the wellbore, and you're going to be producing fluids out of the formation. You don't want to do that in many cases. For example, you may be producing the oil or gas of a reservoir. Sometimes that can produce a kick, and that's not going to be desirable in many cases. In some occasions, you may do what is called underbalance drilling, in which you do have your mud pressure, which is lower than the pore pressure, so you'll be around this region. And that's possible in shales, because shales have such a low permeability that even if you have a gradient, the amount of produced fluid is going to be minimal. We're going to see later on that this underbalance drilling sometimes is useful for drilling shales that have problems of instability with the drilling mud. On the other hand, uh, we are going to have an upper bound for this mud weight, and this is going to be related to the breakdown pressure that we have calculated before, for which we have a tensile failure. And we are going to add one more component to this, and this is going to be the minimum principal stress at that location. We'll see this in detail in just a bit. Other practical considerations for the mud window are that if you have the pressure in the mud to be too high, you could damage the formation by infiltration of the drilling mud into the formation. For example, you don't want to do this in a nice reservoir with a high permeability because you will damage that permeability. And also sometimes having a very heavy mud makes the rock stronger around the wellbore, and that causes a low rate of penetration, which is also not desirable. All right, so let's see a practical example of the determination of the mud window. And in this case, we're going to use the examples that we were using before from problems 6.1, 6.2, and 6.3. In these three problems, we determine three values. First, PW shear, which is the pressure at which you will have a very tiny shear fracture around the wellbore. In problem 6.2, we determine what would be the breakout angle for a mud weight of 10 pounds per gallon. And at that point, we do have shear, but it's more or less controlled. An angle of 6 degrees, it's relatively fine for a breakout. The admissible breakout in a wellbore will depend on the type of rock. So we're going to assume in this case that this is an admissible breakout angle and the wellbore is still stable. And in problem 6.3, we determine the value of PV. This is the breakdown pressure. This is the pressure for which we will have tensile failure near the wellbore, at the wall of the wellbore. Okay, so now the question is how we determine the mud window out of these values. Well, I added in this case also the pore pressure and the minimum principal stress. Let's start with the lower bound, which will be the lowest value for the mud window. As you can see from the figure, the value of the pore pressure is quite low. And if you were to be in this region, you will have a breakout angle that will be too high. Here, for this pressure, is already 66 degrees. If you were here, I'm not quite sure what the value will be larger than 66. And for sure, you don't want to have your breakout angle to be higher than 90 for almost any type of rock. So we're going to choose this value as our lower bound. We didn't choose pore pressure because that's a value, it's too low. We'll have significant breakouts for that value. And we will set that as our lower bound. What about the higher bound? Uh, well, let me say something else about PW shear. We could have also chosen PW shear as our lower bound, but as you see, the pressure required for that is quite high, and our mud window will be relatively small, just somewhere over here, if you were to use PW shear. PW shear will be a very conservative lower bound. In this case, we're going to take a little bit more of risk and accept that there's going to be a shear failure, but with a breakout angle which is not too big. That's why we choose this value of PWBO for an angle of 66 degrees. Okay, now let's go to the upper bound. For the upper bound, we determined that PV could be the upper bound for the mud window because any value of the mud pressure lower than PV is not going to result in a tensile failure around the wellbore. So I could go and choose as an upper bound uh, this value of PV. And in this case, I'm going ahead, I'm going to do that. I'm going to assume PV as my upper bound, but we'll talk about what is the influence of S3 in just a bit. So assuming these two values, now my mud window could be anywhere in between these two values. If the mud weight and the mud pressure at this particular depth are in between these two values, then I'm sure that my wellbore is going to be stable. Okay, so for this problem, this should be the solution, but I'd like to go in a little bit more of detail about the discussion of what is the influence of the minimum principal stress and the value of PV. Sometimes those PV could be higher than S3, like in this case, but in some other times S3 could be lower than PV. And let's see what the difference would be. In case number one, as in the case that we have over here, uh, our minimum principal stress, S3, is lower than PV. And let's imagine that for this particular case, we accidentally go into a value of pressure in the wellbore higher than PV. If that's the case, I'm going to create a hydraulic fracture in the wellbore that is going to start at the wall of the wellbore, but because PW is higher than the minimum principal stress, there is a risk that this small tensile fracture induced during drilling is going to grow into a large fracture in the wellbore because the pressure in the wellbore is larger than the minimum principal stress. And in this case, we will have what is called an event of lost circulation. And let me finish this. Okay, and because we create a large hydraulic fracture, our drilling mud is going to go in order to fill that large hydraulic fracture, and that drilling mud that goes into the fracture is going to be lost. And because it's going to be lost, I'm not going to recover all the drilling mud on the surface, so this is going to be to an event of lost circulation, which of course is something which is not desirable. And we do not want uh, to experience such an event when you're drilling, especially when your drilling mud is quite expensive and precious, like for example in offshore conditions. Okay, so as I was saying before, and for this particular example, we chose the value of PV as our upper bound, but I would say that this could be a risky solution, and only if you knew your rock very well and if you trusted your value of the measurement of tensile strength, you could use PV. The conservative solution is going to be S3, the minimum principal stress. And if you remember, we have been calculating the minimum principal stress for a long time. And actually we call that the fracture gradient because that's the lowest pressure for which we have a risk of causing a hydraulic fracture. So here, remember, these two are possible solutions. This one is conservative. This one is a little bit more riskier, but you could do it if you knew your value of tensile strength or if you trusted your value of tensile strength of the rock very well. For example, if you were drilling through a granite rock that you know that doesn't have any natural fractures or very little natural fractures at all, that has a large tensile strength, and you want to push your upper bound or your mud window to a high value, then maybe you want to take this value because it's going to be safe enough to do that. In the event that your pressure in your wellbore goes higher than the minimum principal stress though and higher over a PV, you're going to have a risk of lost circulation. There is another case though, and in this case, it might happen that after you do the calculations of PV might result lower than the value of minimum principal stress. And in this case, if you do happen to have your value of wellbore pressure higher than the value of the breakdown pressure, then you are going to create a drilling induced tensile fracture, but this fracture is not going to grow too large. Why? Because PW is lower than the minimum principal stress. And that means that at a distance from the wellbore, the minimum principal stress is not going to allow that fracture to grow any further because the minimum principal stress is higher than PW. Notice that in the previous case, the pressure in the wellbore was higher than the minimum principal stress. So even if I had the minimum principal stress acting in this direction, it wouldn't be enough in order to stop the opening because the pressure in the wellbore and the pressure inside the fracture will be higher than that value of minimum principal stress. So in this case, then your upper bound for the mud window is going to be the minimum principal stress, and this is still going to be safe. So always your safe and conservative solution is going to be the minimum principal stress. Remember that in case number one, you could go a little bit higher. Of course, that in case number 2, if the pressure in the wellbore is higher than S3, also you have the risks to go into an event of lost circulation. Okay, let's see now how we use this math window that we have determined here with the application for the previous case, and it's conceptually here to a real case and to an application of drilling. So here I have made a schematic of a drilling rig onshore, and in this drilling rig what we're going to do is we are going to drill up to this formation, which is here. And we are going to determine what is the mudway needed for that formation. Let me check the colors I use. Okay, I use red and blue. So I'm going to put my lower bound in red and my upper bound in blue. All right. Notice that here I have gradient. I have density of the, in this case, is going to be the density of the mud. It's a tiny typo here. Let me correct it before we start. This is the density of the mud. Times gravity. Okay. Okay, so let me check again my colors. Okay, red and blue. Now I'm ready. Let's imagine a first case in which the lower bound is relatively constant, and the upper bound is going to be higher than the lower bound, of course, and is relatively constant too. In this case, you could use a mud weight which is the same as you go from the surface to the location in the subsurface. Because if you're drilling this with a mud weight without any control on the pressure on the surface, and then the pressure is just going to be the density of the mud times depth. And in this case, if you have the same mud circulating all the way through the entire wellbore, let me draw the wellbore first. So let's say that we drill the wellbore and the mud is the same in the entire wellbore, then this is going to be a constant here. It's going to be a constant value, and this is a good solution because it's not too low in order to hit the lower bound, but it's not too high in order to hit the upper bound. If that's the case, you could go just with one casing and finish your job and cement your wellbore, and that's the end of the story. Okay, that would be a case that may be applicable for a relatively shallow wellbore, but in general, this is not what happens. What happens is that these bounds, the lower bound and the upper bound, they change with depth, and usually they increase with depth. So let's see what would be the solution for that. So now if we have our lower bound, which is increasing with depth, and your upper bound is also going to change with depth, we are not going to be able to drill with the same density for the entire interval, because at some point I'm going to have to change the density, so I am in between this mud window. So in this case, the best solution will be to start at the highest density which is allowable on surface and go with a constant density mud up to a depth in which that's not possible anymore, and I hit the lower bound. So here on surface, I will be close to having the wellbore to fail in with a tensile fracture. Here, I will have the wellbore at depth to be closer to fail uh, due to shear and with breakouts. And at this depth is at which I cannot drill any further with this constant density mud, and that will be the maximum depth at which I can go. And at this depth, I will have to set the casing and stop drilling at this point because you cannot go any further. The wellbore is going to fail in shear. And at this point, you set up the casing, and after that, now you're able to continue drilling. And let me do this with another color. You will have to now do the same process again. Just go to the highest possible value and then change your mud density now to this value over here. And now with this value, you can go and get up to the point that you desire. And so after this point, you're going to have your new casing, and this is going to be the wellbore that is a result of that second stage. But it is very important to notice here that because of this changing mud window with depth is the reason why we are also changing the casing. And it's very important also to know that it's super important to determine this value of the lower bound and the upper bound accurately and to be as large as possible, because if I was doing a poor job and, for example, I determined the upper bound somewhere over here, now I hope you can see that we will have to use a lot more casing stages in order to do the same job. So we'll have to do this and then case, go again, case, and go again. So probably in this case, with this upper bound, I would need 3 casings, which will be less desirable. It will be much better just to do it with 2. All right, so this is how we will use then the mud window in order to determine and to design the stages in setting casing and setting the casing depth for a given wellbore. A few more things to say over here are that this upper bound, sometimes we calculate it based on the equations that we have seen, like for example PV or minimum principal stress, but it's also very useful after you finish setting a casing, and if you have this is a new well in a new area, you may want to verify if that upper bound is really an upper bound by doing a leak-off test. This leak-off test is going to tell you for sure what is the upper bound and what is the maximum pressure that the wellbore can support before you have a large hydraulic fracture. So if you want to, as we were saying before, to set these 2 values, the lower bound and the upper bound with accuracy, you may want to do a leak-off test in order to determine accurately what this value of the upper bound is. And just one more thing to say over here, it's also very important to determine these 2 bounds, the lower bound and the upper bound, and to try to set them to be as wide as possible with a level of certainty so that we utilize as few casing stages as possible. And making these windows wider is the job of a geomechanicist that works in drilling. And this name, wider windows, actually was coined by Professor Gray here from our department that investigates all the processes that can help you to make this window larger so you use less casing stages. Just to give you an example, we could increase what is the upper bound for the drilling mud window by using something which are called wellbore strengthening material. These are like small particles that help fractures to propagate further out from the vicinity of the wellbore when you're drilling. And by using those, sometimes you can increase this upper bound a little bit more so that you can push the limits of your availability of the mud weight for a given location. All right, so with this, we finished the discussion about the mud weight. And here in my notes, you will find a few more things relevant to this problem.